Welcome to today's presentation. Let's take a closer look at the energy flow circle of a turbine. First, the gas turbine burns fuel to produce high-temperature exhaust gases. These gases are really important because they contain a lot of energy. Next, this exhaust heat is used to drive the heat recovery steam generator, or HRSG. This is a key component because it captures the waste heat and converts it into steam. That steam then drives the steam turbine, which produces additional electricity, making the process more efficient. Finally, the cycle is closed by the condenser and cooling tower, which return the condensate back into the system. This continuous flow ensures that energy is effectively recycled within the cycle, maximizing power output and efficiency. This whole process highlights how we can harness waste heat to generate more electricity, which is a core idea in efficient power plant design. Let's dive into some fundamental concepts that govern how fluids and gases behave in turbines. First, we have PV equals nRT, which is a key equation for gases. It explains how gas expands inside turbine chambers. When pressure and volume change, temperature does too, affecting the work output. Next, there's the energy balance equation. Delta U equals Q minus W. This helps us understand how energy is conserved at each stage of a turbine cycle. How heat added or removed translates into changes in internal energy and work done. Moving on, we have the Brayton cycle, which is typical for gas turbines. The efficiency formula eta equals 1 minus 1 over Rp raised to the power of gamma minus 1 divided by gamma. This shows how the pressure ratio impacts efficiency. Higher ratios generally mean better performance. Similarly, for steam turbines operating on the Rankine cycle, efficiency is given by the difference in enthalpy between certain points, H1 minus H2 over H3 minus H4. This highlights the importance of energy transfer processes within the cycle. Finally, Bernoulli's law states that the sum of pressure energy, kinetic energy, and potential energy per unit volume remains constant along a streamline. This principle connects the flow speed, pressure, and height, which are all critical in analyzing fluid flow in turbines and pipelines. Understanding these core principles helps us see how thermodynamics and fluid mechanics underpin the design and operation of turbines, ensuring we optimize performance and efficiency across different systems. Let's delve into some key design considerations for our system. First, the pressure ratio and turbine inlet temperature are crucial because they directly govern the efficiency of the cycle. Higher inlet temperatures and optimal pressure ratios help us extract more work from the steam. When it comes to steam parameters in a Rankine cycle, we're typically looking at pressures between 80 and 160 bar, and temperatures ranging from 500 to 560 degrees Celsius. These ranges are chosen to maximize efficiency while maintaining operational safety and equipment durability. The heat recovery steam generator, or HRSG, usually approaches the temperature difference at about 25 degrees Celsius. This small approach temperature indicates efficient heat transfer between the hot gases and the feedwater, which is essential for maximizing energy recovery. For condensers, we aim for a vacuum around 0.09 bar. Creating a deep vacuum reduces the back pressure on the turbine, thereby improving overall efficiency and power output. Finally, it's critical to select the right blades, seals, and materials, adhering to standards like ASME and API. Proper material choices ensure durability and safety, especially under high temperatures and pressures. All these design considerations tie back to our overarching goal, optimizing performance while maintaining reliability and safety across the system. Now, let's walk through the key installation steps to ensure everything runs smoothly. First, we start with the foundation and laser alignment of the base skid. This is crucial because a precise foundation sets the stage for the entire system's stability and performance. Next, we move on to grouting and checking the tension of the anchor bolts. Proper grouting and tensioning ensure the skid is securely anchored and can handle operational stresses. Then, we connect the lube oil and cooling systems. Proper connections here are vital for maintaining optimal equipment functioning and preventing overheating. After that, we conduct a piping hydrotest following ASME B311 standards. This step is essential for verifying the integrity of the piping system and preventing leaks. Following the piping test, we perform electrical synchronization and instrumentation calibration. This synchronization ensures all electrical components and instruments operate harmoniously, which is fundamental for control and safety. Lastly, we carry out a comprehensive commissioning test, including vibration analysis, load testing, and heat rate verification. These tests confirm that the system operates efficiently, safely, and within the designed parameters, tying everything together in the overall success of the installation. Now, let's talk about operation and maintenance. First, we closely monitor key parameters like oil pressure, exhaust temperature, and vibration levels, keeping vibration below 4 millimeters per second. This helps us ensure the equipment is running smoothly and efficiently. We also use SCADA systems for real-time monitoring and alarm response, so any issues can be addressed promptly before they escalate. Condition-based maintenance is a critical part of our strategy. By regularly checking oil quality, vibration patterns, and thermography, we can predict and prevent potential failures, rather than just reacting to them. Lastly, we have specific maintenance intervals: minor maintenance every 8,000 hours, hot gas path inspections at 24,000 hours, and major overhauls at 48,000 hours. These intervals are designed to maximize equipment lifespan and reliability, aligning with our overall goal of optimizing performance and minimizing downtime. Now, let's take a closer look at the applications and the codes and standards that guide our work. When it comes to applications, our solutions are versatile and critical across various industries. For example, in power generation, we work with combined cycle gas turbines, specifically 500 MW blocks, which are highly efficient and vital for electricity supply. We also serve the petrochemical sector, providing cogeneration systems that produce both process steam and power, helping optimize energy use and reduce costs. Additionally, our technology is essential in oil and gas operations, particularly for compressor drives and reinjection units, ensuring smooth and reliable operations. Moving on to the standards and codes, adherence is crucial for safety, reliability, and compliance. We follow the ASME codes, such as Section I for boilers, Section VIII for pressure vessels, and B311 and B313 for power piping and process piping, respectively. These standards are fundamental in ensuring our equipment meets rigorous safety and performance criteria. We also align with API standards like 611, 612, and 616, which are specifically tailored for turbine and compressor equipment in the oil and gas industry. Beyond that, standards like NFPA 850, ISO 45001, and IEC 61511 guide our safety systems, occupational health, and safety management. Lastly, regional and local standards such as Saudi SBC, RC Jubil and Yanbu, SAES, and SEC PPD are integral to our compliance in the Middle East. Overall, these applications and standards form the backbone of our operations, ensuring we deliver safe, efficient, and compliant solutions across the industries we serve.